Today I'm going to talk about revisiting the problem of object recognition. And I'm going to make the case that to move forward, you probably need to take a step back. So what do I mean by the problem of object recognition? For this purpose, it's like we want to understand the transformation happens in the brain when we see a natural image or a naturalistic image. And so there are mostly two main approaches so far. One is the classical approach. You probably all know about that. Starting from human and visual studies, like they will break down the naturalistic process, naturalistic image, to the constituent features like edges, curvatures, and objects. And so, and those encoding features were used as, or is currently used as the stimulus. So you see that the problem with this approach is that we never get to see what those encoding features are going to get processed in the whole naturalistic process. We just know about how those features are going to process. But the obvious advantage of this method is that these features are interpretable. The other approach gaining interest from 2014 was that, okay, now we have deep nets, and deep nets can give us the encoding features. They work on the whole naturalistic image, whatever you give them, and then they give you the encoding features, and then you can compare their features to the features extracted by the brain and give a similarity score, right? And so, what happened to our hypothesis? So now our hypotheses are going to go to the deep net design parameters. What architecture we choose, what objective function, what data domain to train the model, what learning group. And so now we're going to just briefly see what does the similarity mean here. Like you actually show the same image that you show to the monkey, to the deep neural network, extract the features, so these are the neural population, and then for the next image, and then for the next image. And then you compute the pairwise similarity as discussed in Nathan's talk, and then you give a score to that feature explaining the brain. You change your hypothesis about the deep net, you get a new deep net, you get a new set of features, you get a new score. Another score, and the score, the highest score gives the hypothesis set of features on your design parameters. It's most likely to be the better model of the brain, right? But what's the problem with this approach is that the features are not interpretable, and for the first talk, like interpretability is a loaded term here, but I'm going to make the case and say that this is a problem for deep nets as illustrated in this slide. So these are two models in BrainScore. BrainScore is a website that you would just send your models or data, and then you get the score of the similarity. Very helpful, and I think it's the best. It's the first stepping stone to have the kind of thing that machine learning builds on for neuroscience, right? But I'm going to highlight here one problem with this interpretability issue of the deep net approach. See, there's this model, and I really appreciate that they actually put the design parameters of the model here. And so these two models are two very different models on every single parameter, and they give us the exact same number for V4, for explanation of V4. As a modeler, I would just be I would just be baffled. Okay, which of these design parameters give me this number? Which of these parameters I need to push forward to get a better model of V4? And so that's the problem of interpretability that I'm referring to, right? Now, so we have these two approaches. Each of them have a problem and have a advantage. And now I'm going to introduce an analysis method. So it's not an image computable model, it's just an analysis now, just to know, just to be able to get an idea of what happened with the data to make sure that we have the second round of the modeling. Don't worry about the name, it has space similarity analysis. Let's see what it actually does. So first I'm gonna just briefly introduce the data. You probably have already seen this data. Data provided from the Carver Lab at MIT, a heroic effort by Hao Wang and Najib Majad. More than 5,000 images from 64 objects and 8 categories, different sizes, positions, views. And then the data was recorded from multiple regions in the brain, B4, PIT, CIT, and AIT. And a lot of insightful work on this data have been published before. So I reanalyzed this data. First of all, before getting to the interpretable features, I just want to have a control, right? I picked resonance 50, illustrated very simply here by these 5 layers, layer 1, 2, 3, 4, and the average pool. And I took these features and I computed the similarity, just the RSA similarity, CKA similarity. And then what we're going to see is that at each time, which is time from stimulus onset, in each brain area, I computed the similarity of that feature space to the features of the neural data in each brain area over time. So the variation only comes from neural data, no time in the model, right? So, like I said, we want to see first the resonance 50. 5 layers of resonance 50 are trying to explain each of these, the temporal dynamics in data from each of these brain areas, before posterior IT, central IT, anterior. And don't worry about all these wiggles. I kept only the best explanation from this model, layer 3, 4 before, and layer 4 for the rest of the IT. Now, I promise we want to have an interpretable feature explaining the same data. So let's go through that process together. We have these images that Monkey saw, and we want to have the interpretable features. So one hypothesis would be that which brain area encodes detection of the objects. And so you simply put scores. This is a standard practice in machine learning, right? These are the detection masks. So it encodes the size and the position of the objects. And I simply pick these as my features, just that, the labels. And what we're going to see is that how well these simple features can explain neural data in each of the brain regions. So as we can see, the monkey still looks at the whole image. So we have the study natural image processing, and we can say that it's interpretable features. It can get simpler. And so this is the size and position of the detection mask explaining each of these areas. And as you can see, it does a decent job for posteriority, going a little bit above than the explanation for resonance 50. And I put his brain here to emphasize that monkey still looks at the whole image. And so, what about other hypotheses? This is a good thing that we can, about interpretability. Now we can continue our hypothesis space. Now, very naturally, we go and ask, okay, what happens if we have the more detailed shape, like the segmentation map? And we see another set of curves corresponding to that feature. And we can see still posteriority is a better explanation. Let's have both of these features here and see like still the yellow, the size and position a little bit better in posterior IT, but now central IT is better explained by the shape and position. But it looks like that we're out of juice in anteriority. But what is it that anteriority is coding? We can still get like creative and think about, okay, we've seen phase patches and all the abstraction that happens in phase domain over phase patches. Maybe what anteriority does is something more abstract. That is, when monkey actually sees these images, more abstracted version of these images, like the centered view of the object, is what's encoded in anteriority. So let's see. This centered view can explain anteriority or not. And as you can see, it does a pretty good job in explaining anteriority, but mostly in the later part. Still, the first earlier responses are better explained by the resonant 50. And so to have them all together, we see that we have this nice intuitive gradient of features for explaining IT parts, which really we didn't have that even considering the classical approaches. What about V4? Are we going to just give up on V4 and see, like, take these features? So one information that we had about the recording was that, like, the V4 array was only able to, like, the neurons that were here were only able to look at the foveal part of the image, 2-degree foveal, to be precise. And so what I did was that I simply took out all the rest. And so, like, okay, let's give it a go and see whether V4 just doesn't probably cares about objects, just what sees within the receptive field. And yeah, we get the highest boost for the V4 here compared to the other interpretable features. And so let's have a overview of this. As we can see that mostly still the first part of the response is best better explained by resonance 50, but the later, as we go later in time, we get the interpretable features higher. And I think this is a good point to mention that I'm sure that there is a model out there that explains like everything, but better than this. But that was not the point. Just to get an intuition of what happens during in the neural data to get insights for the next round of the modeling. And so now what I'm going to show is the first step toward that next cycle of the modeling. So I took the standard resonant and I pushed this part, like the before receptive field, through this resonant 50. And these are all the explanation provided by that model compared to the standard. We see a lot of improvement. So if we have a model that actually looks at the phobia, it's better at explaining before, and probably a lot of models that we see that actually provide better accounts for B4 and brain score, probably they develop more of a foveation. That's why we see that. And so I submitted this very simple resonant 50 that looks at different foveal regions to brain score. And for the past 2 years, it ranked 1 in for B2 and B4, and overall rank 3. Just as the humble result. So yeah, okay, cool. We can do, so this is the summary of the things that I wanted to share for today, that using this method, we gain insight into the abstraction over time happen in each of these brain regions, and also abstraction over space for the whole object of processing, compared to the standard Dinan approach for the brain. And one finding was that previous work showed that the category orthogonal representation increases from like early areas to IT, and like it would have been assumed that all the way. But then if we break down IT parts, we see this abstraction away, just like we saw for faces. So why stop at brain data? As a way of just ground truthing this method, I've tried to recover what we have already known about the models using this approach. And so this is just a summary slide from some of the work that I've done on models. Like I recovered the shape bias for the stylized resonance 50 and self-supervised bias model, and the low frequency bias in robust neural networks. And using the same method, I proposed some explanation for why we see unified representation across many different models. And lastly, I'm going to thank Elias, Isa, and Nico Corte for their helpful inputs on this work, the Color Lab for providing the data, and funding agency. And one more slide, that was the natural image that I showed in the beginning, was from Charlie Groff. This is the monkey that he was recording from, and this is the famous toilet brush that was the first complex object that showed anticortex response to complex objects. Thank you.